What if I told you that um, the exact same cosmic phenomenon that paints those beautiful, peaceful northern lights in the night sky is actually, well, secretly the biggest existential threat to the modern internet?
It sounds like science fiction, right? But it is absolutely true.
Yeah, because usually, when you think about auroras, you picture this serene, almost magical experience for you and your family. You're bundled up in the snow, looking up at ribbons of green and purple dancing overhead.
Exactly. It feels like this beautiful gift from the cosmos.
Right. But the reality is completely counterintuitive. That beautiful glow is actually the byproduct of an astrophysical event fully capable of causing an internet apocalypse, like literally destroying the submarine communications cables that keep our modern world online.
It really is a staggering contrast between perception and reality because our atmosphere protects us from the direct physical hit. We're basically just treated to a light show.
We get the pretty colors.
Right. We rarely stop to consider the massive, violent magnetic collision occurring just above our heads.
And that is exactly the mission for today's deep dive. We are looking at a single, incredibly comprehensive source today, a compiled Wikipedia article simply titled List of Solar Storms.
It's a fascinating document. So much history in there.
It really is. So our goal today is to move past those pretty pictures and actually understand the real mechanics of space weather. We're going to look at how our stars' temper tantrums have secretly shaped human history and why, in our hyper-connected modern era, these storms pose a genuine threat to the daily routine of everyone listening.
Because it's not just about satellites, it's about everything you rely on day to day.
Exactly. Okay, let's unpack this. What exactly is the sun throwing at us? I mean, what is a solar storm?
Well, to understand the threat, we have to establish the basics of heliophysics, right?
Right.
Which is just the study of how the sun affects its surrounding space environment.
Okay, so the local neighborhood.
Basically, yeah. So when we talk about a solar storm, we're looking at a specific sequence of events originating from disturbances on the sun's surface. The data highlights a few main culprits here. First, we have solar flares, which they erupt from active sunspot regions.
Right, the bright flashes you see in the telescope imaging.
Exactly. Then we have coronal mass ejections,
No.
commonly abbreviated as CMEs. And occasionally, these disturbances can originate from areas called coronal holes.
So those terms definitely get lumped together in sci-fi movies,
Mhm.
but the distinction between a flare and a CME is crucial here, right?
Absolutely. They are very different mechanisms.
Because the way I was visualizing it as I read through the timeline, it's like firing a massive cannon. The solar flare is the flash of the muzzle. It's this intense, localized eruption of pure electromagnetic radiation, like X-rays and light.
Right. And because it's just light, that flash hits Earth in just 8 minutes.
Wow, 8 minutes.
Yeah.
But the coronal mass ejection, the CME, that's the actual projectile, right?
That analogy sets the stage perfectly, though. We do need to adjust the projectile itself just a bit.
Okay, how so?
Well, if a solar flare is the flash of the cannon, the CME isn't, a solid iron cannonball. It's a billion-ton invisible cloud of magnetized plasma tearing through space.
A billion tons of plasma, just barreling toward us.
Yeah, and it takes days to arrive, not minutes. And when that giant magnetic cloud collides with Earth's own magnetic field, it doesn't punch a physical hole in the ground.
Right, it's not an asteroid.
Exactly.
Right.
Instead, it wraps around our planet and squeezes. That magnetic squeezing is what causes a geomagnetic storm.
And the hazards listed in this compiled data for those storms are terrifying. I mean, we're talking about large-scale power grid outages, severe disruptions, or total blackouts of radio communications and GPS.
Dangerous radiation levels for high-latitude aviation, too.
Yeah, and critical threats to human spaceflight. I mean, it's a huge list.
It is. And if we connect this to the bigger picture, the vulnerability really comes down to planetary geometry. There's this phenomenon documented in the data called the Russell-McFerrin effect.
Oh, yeah, the seasonal thing. That blew my mind.
It's wild, right? It explains why large solar storms actually hit us much harder near the equinoxes. So specifically in September and March.
Wait, so the sun is somehow a better shot in the fall and the spring? Like, it aims better?
Well, no, it's not about the sun's aim at all. It's actually about our planet's posture.
Okay, posture. Makes sense.
Yeah, so during the equinoxes, the geometry of Earth's axial tilt aligns our magnetic field in a way that makes it highly vulnerable to the solar wind. Magnetic fields have direction.
like a north and south pole.
Right. So when the incoming solar magnetic field has a southward orientation, it connects incredibly efficiently with Earth's northward pointing field.
Oh, I see. It's like taking two bar magnets and snapping the opposite poles together.
That's the perfect way to visualize it. And that magnetic connection temporarily strips away some of our atmospheric shielding and allows all that violent solar energy to just, well, pour directly down into our upper atmosphere.
So we are literally leaning into the punch twice a year.
Unfortunately, yes.
And the reason you, the listener, need to care about this celestial geometry is that human civilization has never been more reliant on the exact technologies that magnetic squeezing disrupts.
Not even close. We are entirely dependent now.
Right. If a massive storm hits, it doesn't just mean your phone's GPS glitches. It means the global supply chain, which relies on satellite timing down to the microsecond, grinds to a complete halt.
And knowing the scale of our modern vulnerability really forces us to ask a critical question. What is the absolute upper limit of the sun's power?
How bad can it get?
Exactly. To find out if a storm could completely dismantle our infrastructure, scientists had to look far past the timeline of human records. Because, if we only study the last 200 years of the electrical age...
We might just be observing an unnaturally quiet period in the sun's history.
Precisely. 200 years is nothing on a cosmic scale.
So they had to rely on proxy evidence. They basically scoured the Earth for traces of ancient solar storms locked in the environment itself. The timeline is filled with these things called Miyake events.
Yes, Miyake events. They're incredible markers.
And they find them in ice cores and tree rings, right? The mechanics of how scientists read this proxy data is just fascinating to me.
It really is. It comes down to high-energy particle physics. When an extreme solar storm hits Earth, it bombards our atmosphere with cosmic rays.
Just slamming into the air.
Yeah. These high-energy solar particles smash into the oxygen and nitrogen atoms in our upper atmosphere, completely shattering them. This violent atomic collision creates radioactive isotopes, specifically carbon-14 and beryllium-10.
And those just rain down on us.
Basically. The beryllium-10 precipitates down in the snow and gets permanently trapped in polar ice cores. And the carbon-14 is absorbed by trees all over the world as they photosynthesize.
So it leaves a permanent, chemically altered ring in the wood for that specific year.
Exactly. It's like a cosmic fingerprint.
And that chemical signature literally solves an archaeological mystery. This is one of my favorite parts of the article. The timeline notes a massive solar storm that hit Earth in the years 993 to 994 CE.
Ah, yes, the 993 event.
Yeah, it caused a massive global spike in carbon-14, and scientists found ancient wood from a Viking settlement in Newfoundland, Canada. By finding that specific 993 CE solar flare ring in the wood, and then just counting the normal tree rings outward to the bark.
They proved conclusively that Vikings were cutting down trees in the Americas in the exact year 1021.
Which is insane.
Yeah.
A massive sneeze from the sun 1,000 years ago gave us the exact date of European arrival in North America.
It is an incredibly elegant application of astrophysics to human history. It really bridges the gap.
It totally does.
But, while the 993 event was massive, the proxy data reveals events that absolutely dwarf it. For instance, the first identified Miyake event occurred in 774 to 775 CE.
Oh, right. The big one.
Yeah, it produced the largest and most rapid rise in carbon-14 levels ever recorded in the current geological epoch.
Yeah.
I mean, if an event of that magnitude occurred today, the sheer amount of atmospheric ionization would be catastrophic for our entire low Earth orbit infrastructure.
Wait, I'm actually confused by one of the dates in this proxy timeline. Can we talk about that for a second?
Sure. Which one?
There is an event from 7176 BCE discovered via a massive beryllium-10 spike in the ice cores. The data suggests it might have been even stronger than that 74 CE event.
Right, the 7176 BCE anomaly.
But it explicitly notes this extreme storm unexpectedly occurred near a solar minimum. I thought the golden rule of space weather was that these megastorms only happen during the solar maximum when the sun is, covered in sunspots.
You have zeroed in on a major ongoing debate within the astrophysical community right there.
Oh, really? So it's not settled?
Not at all. The 7176 BCE anomaly completely challenges our understanding of solar dynamo theory.
Okay, what is the dynamo?
The dynamo is the mechanism inside the sun. It's basically a churning ocean of electrically conducting plasma that generates its magnetic field. As the sun rotates, that plasma twists and tangles the magnetic field lines until they become so stressed they snap.
And that snapping releases the flares and CMEs.
Exactly. That tangled chaos is what we call the solar maximum. During a solar minimum, those magnetic lines are supposed to be organized and untangled.
Meaning a quiet, well-behaved star.
Precisely. The fact that an explosive event of this magnitude occurred during a minimum suggests our models are incomplete.
That's unnerving.
It is. The data highlights research comparing our proxy records with observations of other stars similar to our sun, and this comparative data suggests the sun might be capable of producing what they call super flares.
Super flares, that sounds bad.
Very bad. We're talking events up to 1,000 times stronger than anything in the recorded historical era.
1,000 times.
Yeah. Now, to be fair, other researchers using different models argue against this, so the debate remains open, but the 7176 BCE anomaly proves a terrifying point. Extreme events do not politely wait for the peak of the solar cycle. They can strike when our guard is entirely down.
Wow. Okay, so proxy data locked in ice and wood is one thing, but the danger shifts from theoretical to, like, visceral when human technology enters the chat. The timeline of extreme events moves from ancient tree rings to the Victorian era, September 1859. The Carrington event.
This is the historical benchmark. By most measurements, it is the most extreme geomagnetic storm ever documented.
It's the one everyone talks about.
Right. And when that Carrington CME slammed into Earth, the impacts were instantaneous, and they beautifully illustrate the mechanism of geomagnetically induced currents, or GICs.
The telegraph network essentially became a victim of Faraday's law of induction.
That is exactly the mechanism, yes. Faraday's law basically dictates that when a massive magnetic field moves over a long, continuous piece of metal, it physically pushes the electrons inside that metal.
It generates rogue electricity out of nowhere.
Exactly. And the longer the wire, the more voltage is generated. The telegraph network of the 1850s was just this massive web of incredibly long copper wires stretched across continents.
That explains the telegraph stations catching fire. I was wondering about that. They were essentially giant antennas soaking up that rogue electricity.
Yes. The operators were getting physically shocked by their own equipment. It was completely unprecedented.
And the magnetic distortion was so violent that auroras were visible in tropical areas, right? The article mentions people in the Caribbean were waking up in the middle of the night thinking the sun was rising because the sky was glowing bright red.
It must have been terrifying for them. For decades, the Carrington event was treated as an extreme outlier, like a once-in-a-millennium fluke.
But it wasn't.
No, as the 20th century timeline proves, it was simply the first time our technology was advanced enough to feel the hit. We continued building longer wires and more complex grids, and the sun just kept firing.
And like the May 1921 storm.
Right, that one produced the farthest equatorward aurora ever documented, burning out telephone stations and causing total communications blackout.
And then we reached the space age. Here's where it gets really interesting, because as our technology becomes more sophisticated, the bizarre, unintended consequences of these magnetic impacts just multiply.
They definitely do.
In August 1972, a solar storm produced the fastest CME transit time ever recorded. But the most staggering detail to me is what it did to the United States military during the Vietnam War. This solar storm accidentally detonated dozens of magnetic-influenced sea mines underwater.
The mechanics of that detonation are just a perfect example of space weather masquerading as a terrestrial threat.
How does that even happen?
Well, those sea mines were equipped with magnetic anomaly detectors. They were designed to sit on the ocean floor and basically wait for the massive, localized magnetic disturbance of a steel ship passing directly overhead.
Oh, I see. But instead of a submarine.
The entire planet's magnetic field fluctuated. The CME distorted Earth's magnetic field so abruptly that the sensors inside the mines interpreted the space weather as an entire fleet of steel ships passing by all at once.
That is wild. The sun literally swept a minefield from 93 million miles away.
It really did. And this violent distortion brings us to a crucial measurement metric used throughout the data: the DUST, or Disturbance Storm Time Index.
Yeah, the DUST pops up constantly in the modern records. What exactly is it?
It is measured in nanoteslas, and it's basically a mathematical calculation of how much Earth's magnetic field is being squished and weakened by the solar wind. A negative number indicates the field is being compressed.
Okay, so lower is worse.
Right. A routine, mild geomagnetic storm might register around negative 50 nanoteslas.
Which puts the infamous March 1989 storm into terrifying perspective. The DUST for that event plummeted to an estimated negative 750 nanoteslas.
The magnetic squeezing was profound. In just 92 seconds, the geomagnetically induced currents surged through the long transmission lines of the Hydro-Quebec power grid.
92 seconds? That's no time at all.
No time. And the rogue electricity tripped the fail-safes and circuit breakers across the entire province, plunging millions of people into darkness for 9 hours in the freezing Canadian winter.
So the Quebec blackout proved that long, unbroken lines of metal are the most vulnerable things on Earth.
Mm.
But since 1989, we haven't just built more power lines. We've wrapped the entire planet in a delicate metal cage of satellites.
Which completely changes the threat landscape.
Right. We are infinitely more vulnerable today than we were during the Quebec blackout. The 2020s are showing us that our orbital infrastructure is sitting directly in the crosshairs.
Absolutely. Because the primary vulnerability in low Earth orbit isn't just electrical interference, right? It is physical atmospheric drag.
Wait, drag. In space.
Well, low Earth orbit isn't a perfect vacuum. When a massive solar storm hits, the intense radiation physically heats the Earth's upper atmosphere.
Yeah.
Just like a hot air balloon, that heat causes the atmosphere to expand and puff outward into space.
Oh, wow. And a very expensive lesson in atmospheric puffing occurred in February 2022. SpaceX launched a batch of 40 Starlink satellites.
Yes, the Starlink incident.
The timeline notes this launch coincided with a mild solar particle and geomagnetic storm of otherwise little consequence. But because the upper atmosphere had expanded from the heat of that mild storm, those newly launched satellites hit a wall of dense air where there should have been a vacuum.
It was as if the satellites were suddenly trying to run in waist-deep water instead of thin air.
Exactly. The drag was so intense that all 40 satellites slowed down, lost altitude, and burned up in a fiery re-entry.
Right.
40 satellites wiped out by a quote-unquote mild storm.
And that 2022 event was merely a prelude to a severe escalation in solar activity documented throughout the mid-2020s. The sun basically woke up aggressively.
Yeah, the timeline gets really crowded recently.
In May 2024, Earth was struck by a G5 superstorm. That's the absolute highest rating on the NOAA severity scale, and it was the strongest storm to hit since 2003.
I remember seeing the auroras for that one. It was everywhere.
Right. It was driven by a wildly hyperactive sunspot called AR3663, which fired off multiple extreme flares in a single day, shutting down high-frequency radio signals below 30 megahertz globally.
And the hits kept coming. An October 2024 storm caused another Starlink satellite to re-enter prematurely due to atmospheric drag. Then, moving into January 2026, the data records a severe S4 radiation storm, the strongest of its kind since 1989, pushing auroras all the way down to Spain and Arizona.
This relentless bombardment raises an important question regarding the survival of our modern way of life. The data explicitly connects these recent atmospheric drag incidents and satellite losses to a highly concerning theoretical scenario.
The Kessler syndrome.
Yes, the Kessler syndrome.
The domino effect in space.
Exactly that. Because of the steep increase in satellite congestion driven by mega constellations containing thousands of commercial satellites, our orbital highways are incredibly crowded right now.
It's like rush hour up there.
To survive up there, satellites constantly rely on automated avoidance maneuvers to dodge each other and existing space debris. If a severe solar storm expands the atmosphere, alters their trajectories, and simultaneously knocks out the communication links required to command them.
Oh, no.
Yeah, those satellites become blind, dead weight flying at 17,000 miles per hour. A single high-speed collision creates a massive cloud of shrapnel. That shrapnel destroys another satellite, creating more debris, precipitating a cascading chain reaction.
And if we trigger the Kessler syndrome, you don't just lose satellite TV. You lose the GPS that writes your food deliveries. You lose the timing signals that allow your credit card to actually process a transaction at the grocery store.
It touches everything.
You lose the advanced weather tracking that warns coastal cities about hurricanes days in advance. A cascading collision effectively locks humanity out of space and throws our daily routines back to the 1970s.
The physical infrastructure of modern life is entirely dependent on an environment we cannot control. It's a very precarious position.
So what does this all mean? We've gone from ancient tree rings proving Vikings lived in Canada, to telegraph machines catching fire, to sea mines detonating by accident, to the looming threat of the Kessler syndrome. Are we just sitting ducks waiting for the grid to go down and the internet apocalypse to arrive?
I know it sounds bleak, but it's vital to analyze this timeline not with panic, but with engineering pragmatism.
Okay, so there is hope.
Oh, absolutely. The data is clear. While a Carrington-level storm possesses the raw energy to existentially threaten modern civilization, proper preparedness and mitigation can substantially reduce the hazards.
Also,
It is entirely about building resilience into our systems. We can engineer our power grids with massive capacitors and fail-safes to harmlessly absorb those induced currents. We can design our satellite networks with robust shielding and autonomous safe modes that trigger the moment radiation spikes.
Ah, so the threat is astrophysical, but the solution is terrestrial engineering and international policy.
Exactly. We have to respect the environment we live in and acknowledge that our environment extends 93 million miles away to the boiling surface of the sun. We cannot negotiate with a billion-ton cloud of magnetic plasma.
Right. We just have to build a society sturdy enough to take the punch.
The proxy records and human history both prove that the storms are inevitable. The only variable we control is our readiness.
To close out today's deep dive, I want to leave you with one final thought from the very bottom of this compiled data. We've spent this entire time talking about the storms that actually hit Earth. But there's a small section titled Events Not Affecting Earth, and one date stands out, July 23, 2012.
Ah, the ultimate near miss.
On that day, an ultra-fast Carrington-class CME erupted from the sun. It had the precise magnetic orientation and raw power of a civilization-altering superstorm.
He was a monster of a storm.
But it happened to erupt from a side of the sun that was facing just slightly away from Earth. It tore straight through our exact orbital path, but we happened to be further down the track.
Just a few days off.
Right. If that eruption had occurred just 9 days earlier, when we were in that spot, it would have been a direct catastrophic hit to the modern world. We're essentially spinning through a cosmic shooting gallery where the bullets are invisible magnetic clouds.
It's a sobering thought.
So the next time you see footage of those beautiful, peaceful auroras glowing in the night sky, I want you to remember those fragile submarine cables sitting at the bottom of the ocean. And ask yourself, what happens to your daily routine, your bank account, and your connection to the people you love the next time the sun's aim is a little more accurate?